Hello, my name is Daniel Marti. I'm working full-time on the Q project, a new config language. And there are a few of us that made it along today, so if anybody wants to talk about Q or the Go project, you can find me later. I might run away a little bit, but I'm not that shy. So I'm going to talk about Go's build system. And Go is well known for a few reasons. First, sometimes it's a little bit weird. Go path, what is that? That is the first question anybody asks when they learn Go. What is modules? Why is it so different from every other language? There's no lock file. It's not built on top of LLVM, which is a trend for a lot of these modern compiled languages. And another reason why Go is known is because it builds fast. And let me show you what I mean by that. So let's make the font quite a lot larger. +++++. So when you're in a checkout of Go, this is Go master as of yesterday, today. I can enter the source directory, which is where the code is. I'll make that slightly bigger. And I can time a build of Go itself. And this is a laptop that's not impressive by any means. It cost me like £900 2 years ago, so it's not fantastic. And you will see that it builds Go pretty darn fast. So in this case, it's bootstrapping Go by building the toolchain twice, and then building all of Go, including the standard library. So it actually builds the toolchain 3 times in total. And it does all of this, as you can see, pretty darn fast on a laptop that's running on battery. And it should finish in about 50 seconds, unless the demo gods are not very happy with me. And the basic idea here is to prove 2 things. First, yes, builds are fast, but the Go toolchain is also pretty small. You can see that part of the reason why it builds so fast is because it's not building that much code. And it should finish any moment now. So now it's building the packages as in the standard library. It's going to take a bit longer. So you can see it built Go. And if I do Go version, you can see that's the same version that, from yesterday. It says August 16th. And it took 53 seconds on battery. Not bad. So if we go back to the slides. So the weirdness and speed are not coincidences, not by a long shot. The first reason why Go is fast is the language itself. It deliberately left out some features like templating for generics. So when you build a piece of Go code, it's not going to balloon into 10 times the size or anything like that in general. The toolchain as well, it doesn't use something like LLVM. These compiler libraries are very powerful, but also complex, and sometimes a bit slow. And Go's toolchain is very much skewed towards speed, as opposed to producing good code. It still produces good code, but not as good as like GCC or LLVM, because they try much harder. It's a different trade-off. Another example is dependencies. So minimal version selection which is the algorithm that makes Go modules find what versions you're going to use of your dependencies. It's cheap to compute. And I'm not going to go into that right now, but we're going to come back to this later. So the design was clear from day one, but how does building actually work? So let's go back to our terminal. And I have prepared a very simple demo. So you can see we've got a main.go. All it does is print hello, and Go mod that just says a test module, nothing particularly interesting. We can do Go, if I don't typo it, we can do Go build. And then I can run it. So if I do test, hello there, it works, amazing. So we can do Go build -v to tell it what is it building. In this case, it's building nothing because it's fast. But we're going to go back to how that caching happens. But if we do AV, A meaning please rebuild everything, you can see that the V flag then tells us what is being built. We can also use the X flag, which is going to spam us with a lot of stuff. And I'm just going to let it do its thing, and then we're going to look at it for a second. So essentially, the X flag is sort of like Bash's X setting, as in it's showing us all the commands that it's roughly running. I say roughly because the Go tool is not a script, right? So it's not actually executing this as a shell, but it's showing you more or less what it's doing. So you can see, for example, it finished by linking a binary, like in many other compiled languages. But if we go a bit further up, we should see the compiler somewhere. Yeah, there we go. So in this case, the compiler is building the main package. So you can see that it's running these little tools underneath, under the hood. So command go, when you run go build, is the main program you're running. It's our entry point. And underneath, it invocates other tools, such as the compiler and linker. So it sort of like orchestrates your entire build, akin to a makefile in other languages or other build tools. But command go actually has a ton of features. If we ignore big chunks of the toolchain, like the compiler and the linker for a second, because I am not an expert in compilers or linkers, command go itself, before it even calls those, has to do quite a lot of heavy lifting. So this is what this talk is going to dive deep into. And this is going to be quite a lot of information, and I'm going to go pretty fast through the slides because I don't want to bore you all to death. But the slides will be posted later, so if you are particularly interested in any particular slide or topic, you can always follow the links, read later, and so on. So the first one that it does is package patterns. And it's one of those things that's slightly weird with Go, in that you can do, for example, go build ... and then it builds a set of packages, or maybe 0 packages, depending on what it matched. It's sort of like globbing, but not really. So in this case, in a project, with 2 packages, it might build the package foo and then foo bar if they're both under your current directory. So the short version of how patterns work is that /prefix means relative to where I am right now, and ... matches anything. And matches anything, there's a lot of hidden dragons in there, because what if you do go build ... What does that match? The universe? So it's a bit tricky, but in general, nobody would do that. So in general, it's prefix / ... or ... / and then something, right? So then it's a little bit easier to understand. And if you want to learn more about how patterns work, go help packages. And I'm not telling you to go help some packages. I'm saying this is the help documentation for how that works. The next thing it does is perhaps obviously is loading packages, because calling the compiler is all good, but the compiler consumes Go files, and when you run go build, you give it a package path. So in between those two things, it needs to figure out what it needs to compile, right? So if we do, for example, go build ... If we do go build ... essentially what it ends up doing is, if there's a Go package in the current directory, meaning if there's any Go files to be built, it will list them, and then it will read them, right? And one of the first things it needs to do before it actually compiles the current package is it needs to find all the dependencies of this package, right? Because you need to generally build dependencies, your dependencies, before you build yourself. At least that's how Go works. So in this case, it looks at the import declarations. In this case, my package is importing FMT, or FMT. So the next thing it does is it needs to find FMT. So the first thing it does, at least in the Go path world, is this a standard library package? If so, I'm going to look for it in the Go root directory, which is roughly where you cloned Go itself, or where Go was installed. And if it's not there, it's going to look into your Go path. So it would be go path / source / github.com / steve / foo for whatever project, right? So what it will do then, when it has that directory, is again list those files, read those files, and then recurse until it has all the packages in the import package tree that it needs. And it essentially keeps doing this until it's done, right? And it will, of course, if 2 packages import the same package, it will not redo that work. It tries to do as little work as possible. And what if a package is not on disk? Because I've talked about looking at directories, but in reality, when you run go build, not all of the dependencies might be on your file system. Maybe it's a new machine. Maybe you cleaned the caches and so on. So with go path, the answer was, well, you need to run go get manually to fill your go path with all the packages that you need. But now we have Go modules, and modules are quite different, mostly for a good reason. So we are, if we imagine the Go tool as being a little curious gopher, now it's asking us for code, right? It wants to get some code that we have. Maybe I'm trying to publish a library, and I publish it on GitHub, right? So the Go tool needs to fetch that. How does it do that? We don't really distribute packages. We distribute modules. And modules contain packages kind of like how packages contain files. So you can think of that hierarchy. So let's look at a demo again. And so I have another little project here, demo project. The only difference with this project is that it has an external dependency. So it has a dependency on a library that's not in the standard library. In this case, it's under golang.org, but it could be under github.com. It doesn't really matter. And you can see, we have also a module that declares that dependency. So if we do go build, again, it does nothing because it's a lazy toolchain. It doesn't do anything unless it absolutely has to, right? But if we force it, go mod cache. Let's actually export that to make my life easier. And if we do go build, so go mod cache is where it caches the downloads of modules. So if I give it an empty go mod cache, it will do, oh, wait, I don't have it. I have to download it. So how does it actually do that? So what it does is, again, it looks at main.go, it looks at the imports, and it's found, in this case, it's found an import that is not part of the standard library. And because we forced it to use a go mod cache that's empty, it goes like, oh, I don't know where this is. I don't have it. I have to fetch it. So what it does next is it looks at go.mod, and it says a required directive in this go mod file. And it says golang.org/x/mod, and a minimal version for that dependency, in this case 0.5.1. So go mod records those minimal versions, and then go consumes them. And then we need to download them from either go proxy or version control at GitHub. So by default, Go comes with a Go proxy that's proxy.golang.org, comma direct. And this comma is like, it will attempt each one of those list elements. So first it will ask the proxy, and then it will fall back to direct, which means the VCS. So in in Golang's case, it would be googlesource.com, I believe it is. But in GitHub's case, it would be GitHub itself via Git, right? So roughly what it does is it goes to proxy.golang.org, and it uses its REST API to ask it stuff. So you can ask it, please list me all the versions for this module. And in this case, you can see there's quite a few, including ours. You can ask it, please give me the most basic information about one version. In this case, it only tells you what the version name is and when it was published. You can ask it, give me just the module file, the go mod file, because this can be useful for example, doing go mod tidy without downloading all the source. You just need the mod files, really, in general. And you can also ask it, please give me the source code. And the source code is actually a zip file. And zip files, if you're like Linux users, you might think, that's weird, why zip files? And it's because they are pretty much a good fit for what Go needs, which is random access to files, right? If you go for a tarball, like tar.gz, gzip, you generally need to stream or extract the files as you go, even to get just one file. Whereas zips, you can pretty easily just list one file and get it. So we can download it with curl. We can see that in this case, this module weighs about 150 kilobytes. We can unzip it, and the contents are kind of like a Go path. You can see we end up with golang.org/x/mod. But this is where the similarities with GoPath end. Because in GoPath, you could only have one version per package. And if you wanted a different version, you had to overwrite it or create a new GoPath. Whereas in the module world, you can have multiple versions per module, not per package anymore. So in this case, it's a suffix, at some version. And also note that these zips are flat, as in they don't contain the history of that project. They don't contain the, for example, .git directory or .svn. There's multiple reasons for that. The basic one is that Go build doesn't need it. It just needs the Go files to build them, right? And this makes the zip files a lot smaller, especially for long-lived projects with a long history. That makes things a lot faster. So what about go proxy.direct, which is what we saw at the end of that list earlier? You can also use this directly, and it means essentially don't use the proxy. Some people do that for privacy reasons. Maybe they want to talk directly to the code hosting side without going through a central registry server. And what this will do is it will make you clone from VCS, as in do a Git clone or do a SVN clone or whatever else for other VCS systems, version control systems. It should be noted that this is slower because you are downloading all the history. And if you download a zip file, it's just a file that's being cached on a server pretty easily, so it will download as fast as it can. Whereas if you do a git clone and you're talking to github.com, for example, it will need to resolve deltas, it will need to fetch the latest version for you, so it will generally be a bit slower. So the proxy is a good thing in general. And you cannot just clone the URL that you were given. I've seen many people do this with GitHub, and it works with GitHub, because on GitHub, the URL for the project is the same one that you can use for cloning. But in some other cases, it's not. For example, golang.org, it tells you that's the import path, but there's no Git server there. If you try to clone, it's going to fail. So what Go does, what command Go as a build tool does, is it does another HTTP request to the golang.org server at the path of the module. And it says, as part of the query parameters, hey, by the way, I'm go get. In this case, we didn't run go get, but just ignore that for a second. And in the header, in the HTML header of that file that you get as the web page, there will be a bit of metadata that says module golang.org/x/mod is backed up by the Git VCS at this URL. So then you know to do git clone at googlesource.com, right? I'm not going to bore you with more details about how modules works. There's a lot of them. This page that I'm linking to is fairly lengthy, but it also has quite a lot of interesting details, and you don't have to read it all at once. So I would suggest you to check it out later. So now pretty much my favorite topic, and it's caching, because like we said, we're lazy gophers. And if we don't have to do any work, we're not going to do it, and we're going to get a bit chubby, like this one here. So the fastest way to do it, a task, is not to do it at all, right? But you need to know whether you've done it before to reuse it. And Go has multiple kinds of caches. We already saw the module cache in Go mod cache. So where exactly are they cached? There's the, like we said, the Go mod cache directory. By default, it's under your home directory, or where your Go path is, wherever that is. And if we create a new one and we list it, it's empty, of course. And then if we build something and we go look at that cache, it's no longer empty anymore, and it's got a couple of directories. The cache directory, it's pretty much exactly the same thing I showed you from the proxy. So it's like a local cache of those proxy files. And if we look at then a Go path-like directory next to it, it is the unzipping of those zip files. So that is pretty straightforward. And again, you end up with a directory structure that is quite similar to GoPath. It's just that it's not as visible as GoPath. It's hidden in cache directories. And like we said before, note, please remember that GoPath only allowed one version per package. So this is quite a different system. On top of being transparent, you don't have to run go-get to download stuff anymore. It is quite a bit more versatile. Another one that's quite important, depending on your environment, is build caching. Because in many scenarios, caching CPU work is as important as caching downloads. Maybe you have fast internet on a small CPU. Maybe you have 5G on your phone, but your phone heats up quickly, so it can't compile very well. Or you might be on the opposite end of the spectrum. Maybe you've got a very powerful machine, but your internet is DSL, right? So having the two caches is very important. So Go builds code one package at a time. A Go package is what you could call the compilation unit, the building unit. It's the basic building block. And compilation is generally the biggest chunk of a Go build. So for example, if we have a main.go, and we can call this package M for main, and it imports 4 other packages, A, B, C, and D. When you run go build, roughly, if you squint a little bit, what we saw with go build -x is that it would run these commands, right? It would compile each of the packages, running the compiler binary, and then it would link all of those objects together, and linking would give you a binary, and the binary is the result. And because in general, when you run go build, you're compiling multiple packages to end up with one binary, that's the most common scenario, you ideally want to save as much work from this compilation step as you can. So let's go look at our package again. So let's do export go cache. So just like before we did with the module cache, I'm going to tell it to use an empty build cache. And if we run go build, whoops. If we give it the v flag, that's better. So you can see with an empty go cache, it did have to rebuild a package. But if I run it again, it didn't, because the cache has been filled with the compiled package. And how does it do that? I'm not going to go into too much detail here, but there's some other little tools that you can use to inspect how the toolchain does this. And one of them, if I don't typo it, which I most likely will, is go debug. So go debug, go cache, hash equals 1, go build. And this prints quite a lot. It still does a regular build, but it essentially like logs a lot of debug information. And let's look at, for example, the, where's the mod package? Let's look at the fummed package. That's a bit easier. So to be able to cache these builds, caches need a key, right? If the key changes, then you need to redo the work, because that key doesn't exist in the cache. If you have the same key and the key exists in the cache, then you can reuse that work. So in Go's case, the keys are hashes. And here, it's telling you what it's including into that hash for the fummed package. So it's including the Go version itself, because if your Go version changes, it needs to rebuild all these packages. It's telling you what tool it's running. It's telling you what environment you're building for. I'm actually not sure what this line is. Ooh. It's telling you also what build settings you used. These would be like build tags, Go AMD 64, Go ARM, all these build settings that you can set. Changing any of them means that you have to rebuild packages, right? Because the hash changes. And finally, perhaps most importantly, it also includes hashes of the source files of the package. So if any single Go file in that package changes, even by 1 byte, then the whole hash will change, and then you have to rebuild it. And then, because if you rebuild a library, you have to rebuild yourself as well, it will also include the hashes of its dependencies. So it is quite smart in how it does all of this. And in general, you can just ignore all of this, but you can use tools like this one to, you can use flags like this one to inspect what it's doing. So like we said, each package ends up with one of these hashes. Go call them build IDs, but you can call them cache keys if you want. And you rebuild only if the hash changes. And like we said, it includes a bunch of things. I'm not going to repeat them. And if you squint a little, Go's build cache uses hashes in a nested way akin to Git. If you have a Git hash, you know that that source is not going to change, because if anything underneath that hash changes, the hash will change. And then that hash contains other hashes. It contains the history of the Git repo, right? You can say it's like a blockchain, but I'm going to leave it there. It's basically the same. And changing any input at all, even if you change the Go version just slightly, it will still rebuild everything, right? Or at least all the hashes that have changed. So for this reason, something that's a good advice in general is that you should avoid huge packages. Because if you have a package with 1 million lines of Go code and you change just one, you have to rebuild all of them, right? So smaller packages mean better caching, saved CPU cycles, faster builds, and so on. Now, if you look at this graph again, one problem that we have is that linking is a single step, whereas compiling, you can compile one package at a time. You can only link one binary at a time. And we said that the most common scenario is building a single Go binary, right? So you only link once. So if you go back to our demo, you can see that the test binary is there. If I remove it and run go build, it's there again. So let's try running a timed go build a few times. You can see that it's taking 30 milliseconds, which is not much at all. But if I remove the test binary and then rerun that, it took slightly longer because the Go cache is still there. So it doesn't have to recompile any packages. But the binary is gone, so it has to relink the binary. So that's those 50 milliseconds that it took extra. The way binaries are cached is slightly contrived, but the basic idea is that the Go tool embeds the build ID in the binary. So the first thing it ever does is run this command. And build ID is just a very simple tool that will extract a piece of metadata from the binary. And this piece of metadata is the final hash of the whole build. So the Go tool says, I need to build a binary whose hash, I need to link a binary whose hash is this. If it finds the binary is on disk and it has the same hash, it just goes, great, nothing to do, I'm done. But if you change, for example, let's remove this file and let's touch a different file. So now we have another test file, but it doesn't have this metadata, right? And then we time the build again. You can see that it did link again because it didn't find the same hash. If you want to learn more about build IDs, again, before I put you all to sleep, there is quite a lot of interesting information in this file inside the Go project. It has like about 100 lines of documentation, of comments, that explain exactly how these hashes work. And I think it's pretty interesting. Another feature that it has that is fairly well known is parallelism. So in this case, if you've got 4 CPUs, they all help you perform your build, right? And now I lied a little bit when I showed you this diagram earlier, because I said the main package, the package M, imports A, B, C, and D. But you can't build M at the same time as those 4, because M imports those. And the way Go works as a build system is that your dependencies need to be built before you, because that's how it makes the compiling efficient. So the actual graph of what you need to run, where the arrows are, you could say, happens before, lines of how you can go about the build. You first build the 4 A, B, C, D packages in whatever order you want. You could do them in parallel, but then compiling M and linking M doesn't happen in parallel to anything else in this particular example. So bits of command go, command compile, and also the linker are parallel within themselves as well for this reason, because you end up with these bottlenecks. If the linker was really slow, then go build would be really slow because you're just waiting for the linker, right? So the linker tries to use all of your CPUs, and the same for the compiler. So you end up with almost 2 levels of parallelism. You can end up building 4 packages at once, and each one of those compilers will use multiple coroutines at once. Another one that's quite famous is reproducibility. And we can define reproducibility, if I can pronounce it, as when repeated, it produces the same result. So if you run the same build, you should get the same binary, right? So in this case, if our tool is a little gopher and it needs a little piece of carrot, it should end up with in the same state, as long as it's the same piece of carrot. So thanks to build IDs, which are hashes of all the inputs, equal inputs must give equal outputs. In other words, if you don't have this property, you couldn't do any caching at all. If every time you build, you end up with if every time you build the same inputs, the same code, you end up with a different result, you would never be able to cache anything, because every time you would have to start over from scratch. So you do need this determinism, this reproducibility. But something that catches a lot of Go users is that reproducible for you doesn't mean reproducible for others. And I'm going to show what I mean by that. So again, let's start in our demo. If I do Go build, and let's move the binary that we got to test me, and imagine that I build the same binary for my router, which is ARM instead of AMD 64. So I do Go arch equals ARM 64, Go build, and then this will take a little while because it has to rebuild everything. And then we look at what these 2 files have. So you can see that the binary is built on on a AMD 64 machine are different than the ones built for an ARM machine, right? So in this case, if I run Go build over and over again, I will get the same result. But if somebody else runs Go build, they might not, because their build settings might not be exactly the same as the defaults on my machine. And the defaults being you're building for yourself, right? So for universally reproducible builds, and I'm gonna say that this is some general advice. They're broad strokes. Sometimes you might not have to do all of these. Sometimes you might have to do more of these. But in general, you want to use the trim path flag. And the trim path flag says do not include the current directory into the binary. Because by default, if we look at, for example, let's look at the test me binary, what strings it contains, and we grab from my username, you will see that it contains all the absolute full paths to the Go files that it built. So of course, if somebody else called Roger, who has a home directory called home/Roger, builds this, they will end up in a different binary because it has different strings. So you want to use the trim path flag to remove that variable from the build. You want to record what version of Go you used, so everybody has to be on exactly the same version. You have to record what build parameters you used, so if you change your Go arch, if you change your tags, if you change anything else, you need to use the same. And cgo is a big part of this as well. You can either disable cgo, which is what some people do, especially when cross-compiling, or you can make sure that your whole C toolchain is fully reproducible. You can do it, but I'm not going to explain how. I'm going to leave that as an exercise for the reader. And one that's quite trendy lately is supply chain security. And this roughly means that nobody can insert code into your build without you noticing, right? That you can't be hacked by running go build and not notice that something's going on. So all module zip files containing all that source code are hashed, and those hashes are then kept in GoSum, but also something called a sum database, a sumdb. So the sumdb by default is sum.golang.org. It's quite similar to proxy.golang.org. And in our case, in this sample project that I showed, if you look at GoSum, you will see that the xmod module shows up in two places. It shows up as itself. This first hash is the hash of the zip, and also as its Go mod file. And the Go mod file is just the zip of the mod file, right? Not the rest of the source code. And if we ask the sumdb server, hey, can you please give me the hashes for this module at this version, you can see that it's giving us exactly the same hash. So if it gave us a different hash, that would be like a suspicious behavior, right? Because that means that either somebody tampered with my laptop, or somebody's tampering with my internet connection, or something along those lines that's making the two same versions contain different bytes. So because I'm good on time, we're going to do a few quick bonus rounds. And I think we can do maybe some questions about all of this later. I'm going to leave some time at the end. And like I said before, these slides will be published later, so you don't have to worry about remembering a lot of these details. How is minimum version selection cheap as part of resolving dependencies in Go modules? This is a big reason why modules is designed the way it is. Essentially, when you run Go build, and Go needs to resolve what versions it needs to, sorry, no, I said that wrong. When you run Go mod tidy, and it needs to resolve what final versions it's going to do as part of a build, it needs to iterate, right? It needs to see, oh, do I need to upgrade any dependencies? Are all of my dependencies OK? And the way it does that looping is iterating by upgrading at one dependency at a time. It never does any downgrades automatically, or it never loops. It never does like an infinite loop. And there are only a finite number of upgrades you can do in your set of dependencies, unless you have like a magic dependency that has an infinite number of versions, right? And it won't consume that much CPU to run this algorithm because the choices it's making are easy. So in this case, if you have two dependencies, A and B, both at versions 1, and A says, no, actually, I want B version 1.1 or 1.2, then the only thing you can do is upgrade B, right? So there's nothing much to compute. You just follow instructions. If it finds a problem while running that iteration process, it will generally stop and ask you to fix it. It's not a very smart algorithm. It doesn't try to be smart, because if you try to make things smart, it's when they become complex and slow. So it's a delicate balance. But I think the delicate balance that Command Go has struck is that the error messages that it gives you, it tries to make them as intuitive as possible. So when you get an error message, you should generally know what to do to fix it. Another topic that's a bit weird about Go is the lack of makefiles or build scripts. You do see a few sometimes. You do see go generate /assets, or you do see sometimes LD flags, x equals version set to some string. But the good news is that the need for those things is becoming less and less over time. So for example, generating assets, as in embedding assets into your binary, it used to produce these massive files with big strings with like images and stuff like that, encoded as base 64, which was ugly. But since 1.16 in Go, you have Go embed. So you can embed those files directly as part of Go build, and you don't have to run a Go generate step as part of your build. So one less reason to have a build script. Another reason is what I showed you with setting the version to some string, right? Since Go 1.18, the VCS version, so if you run Go build inside a git clone, the version information of that VCS state will be also attached to the binary. And I'm going to show you briefly what that looks like. So let's run Go build again. And what we can do is, so there's a command called go version, like we said before, that shows you the version of Go itself. You can do go version with some binary, and it tells you what version of Go build that binary. But the most interesting one, which is kind of hidden away, unfortunately, is go version -m, and then a binary. And this shows you all the embedded build information that's part of the binary. So it tells you this was packaged with path. The main package has path test. The module is path test, because in this case, it's not a real module. I don't know what version of the module it is, because it's a local module. So it wasn't downloaded through the proxy or anything like that. But I do know what VCS revision I was on when I ran Go build. And I know what the timestamp of that commit was. And I know that there were modified files when I ran Go build, because I was tinkering with this before. And it also embeds the build settings. So actually, to get kind of reproducible builds, all that you need to do is log the version of Go, disable cgo, use trim path, and then just rely on these embedded settings so that everybody else can copy them and just use the same ones. A feature that's quite new, I believe it was added in Go 1.19, released very recently, is for caching of the loading of packages and modules. So I, again, lied a little bit earlier when I oversimplified this graph. You don't go straight from running Go build to compiling Go files. You first need to find those Go files, right? So in this case, you need to find A, B, C, D, but also M. And to load a package, you, like we said, locate the Go files. You parse the package names in those Go files, and you parse the imports, so you can follow the tree of imports to other packages. And then you also need to make those hashes that I showed you earlier with build IDs, because you need those hashes to be able to cache stuff. And in Go 1.19, some of this is cached as well. Don't ask me how it works, because this stuff is not that expensive to begin with. But I believe it uses file metadata or something along those lines. But the good thing with command Go is that it is written in Go, so you could always go poke at it and see how it works. And the last demo that we will do today is a flag that I like a lot, and it's called toolexec. And it's a bit of an escape hatch to insert yourself into Go build. I believe they exposed it for their own use cases while developing the compiler and the toolchain. I found it, I started using it, and then they said, well, you're abusing it in ways that we never saw coming, so maybe we shouldn't have exposed it. Too late, I guess. So something we can do is go build toolexec equals bin time, for example. Why didn't that do anything? Oh, there we go. So I forced it to rebuild everything with the A flag. And what toolexec does is when it calls other tools, other binaries like the compiler or the linker, it will insert your command, your program before. So in this case, instead of running compile foo.go, bar.go, output, package.out.o, it will instead run bin time compile. So in this case, the only thing it's doing is it's timing all the compilations. So you can say, for example, the foamed package elapsed about 100 milliseconds to build. But you can think of many ways to abuse this flag for great fun. You could use it to, I don't know, replace the Go compiler with a different compiler. You could use it to change the Go source code in place. You could use it to, I'm guessing you could even use it to separate a compilation between multiple machines, but I'm gonna leave that nerd snipe in the air to see if anybody bites. And that is pretty much it. There's only a few more things that I'm going to talk about, and that is instrumentation. And I'm not going to explain how these work, but I'm going to mention them. And if it sounds interesting to any of you, you can then go look at how they work. The first one is the race detector. Many of you probably know about this one. It instruments your code as part of a build, so that if there are any memory races when your program is run, it will generally complain about those. The memory sanitizer, or msan, is somewhat similar. It's for finding uses of uninitialized memory. This is generally not possible in Go, but if you jump into CGO, where you can do malloc and then use memory before setting it to something, then you're opening yourself to that kind of memory problems. So the memory sanitizer helps you against that. And the address sanitizer is quite similar. I'm not sure if it's only for CGO, but I'm guessing it probably is. It finds addressability issues. And in general, in Go, you don't really have those because you don't do pointer arithmetic. But if you jump into CGO or you start using unsafe pointers, this might be useful to you. And if you want to read more about how these sanitizers work, they are all part of a Google project. So you can follow that link and read more details. And if you would like to learn more in general about all this stuff that I talked about, or maybe the basics, or maybe some other related topics, I'm going to leave a few ideas here about how you could do that. You could look at the docs for Command Go itself. It's a Go doc page. It has quite a lot of high-level information. You could look at the source code of Command Go itself, because like we said, it's a Go program with many packages. It is a somewhat complicated Go package, or rather set of Go packages, but it's also not rocket science. Like modules doesn't have like a SAT solver or anything like that. If you read the documentation along with the code, it's somewhat easy to follow. And also the commits in master. I find that the commits that get merged into Go have very good commit messages. So for example, whoops, if we look at my checkout of Command Go here, and we do a git log, you will see, whoops, a git log of just Command Go. You will see that the last change was made by Brian Mills at Google. This was written in May, but probably merged yesterday. And you can see that it changes a bunch of things, but without needing to read the code at all, they generally write very good commit messages that tell you what the changes are doing. And not only that, but they have quite good tests. So if we scroll down a little bit, you can see that they have these integration tests that actually show you what it's fixing, which I think is really useful.